Everyone can hear me okay?
Yeah, I think I can hear you.
Okay. Thank you for inviting me. I'm very excited to hear everyone's talks today, and I truly enjoyed Walt's presentation. It was highly informative. My name is Lisa Perez. I'm the Associate Director at High Performance Research Computing, and I'm going to be giving you an overview of the resources that we have that can help you build your digital twin faster. Okay, so at High Performance Research Computing, our mission is multi-level. The first mission is to provide you with computing resources. But in addition to the computing resources, we also provide consulting, technical guidance, training, and support to use the resources. We also love to collaborate on computational and data-enabled research. I want to point out that the services that we provide are free of charge to faculty, postdocs, staff, external collaborators. We have a lot of compute cycles for your research. Application is required to access, but we also have a lot of user services, the help desk, training, advanced training, and you will get access to state and national advanced computing resources. So how does this fit into your digital twins environment? So I've been doing a lot of research on digital twins. It's a very exciting field. I'm trying to bring all the components together. So the multi-levels of digital twins, HPRC, for the most part, fits into 0 and 1 here. And we're hoping to move more into 2 through 5. So the initial building of a standalone twin, where maybe the physical asset doesn't already exist, but you're building a 3D model for it. The descriptive twin, where the asset already exists and you're getting feedback, the all-important feedback to have a more precise and loop that constantly updates the digital twin. Okay. And then the predictive twin, comprehensive and autonomous twin. And this is where, we're more in you need the low latency, so you can have the very fast feedback loop to make decisions on something that's already deployed and active. Okay, so most of my talk is going to be on the 0 and the 1 realm, but moving into the 3 and the 5 in the future. So what kind of compute do we currently have? Grace is our flagship system. We have over 44,000 core, 925 nodes, a good amount of memory per node, 384 gigabytes per node, and 48 core per node. And the accelerators. So we have server grade GPUs, NVIDIA A100s and T4s, along with RTX 6000s, along with the global disk with fast communication between the compute nodes and the disk. Okay? And this is very important when you're first building a large and complex digital twin. We also have Terra. It's our slightly older system, but we still have a lot of core available for it and some accelerators. So beyond the current flagship of building your initial twin, we also have some advanced resources which have new and novel technology in them. So we have an NSF-funded system that is on the floor and powered on, and currently is in beta testing and troubleshooting by the composable provider. So FASTER is the name, Fostering Accelerator, Scientific Transformation, Education, and Research. And what is unique about this system is that it is truly composable in a software-hardware approach. It also has new Intel Ice Lake CPUs in it, and a wide variety of NVIDIA GPUs, T4s, A100s, and we're bringing in A10s, A30s, and A40s. The unique thing about this software is its ability to compose the accelerators to a compute node. Now, historically, composable has been used in the fashion of like Kubernetes, where you take a system and then you split it up and you have a small bit of that system. Whereas with the composability that we have on FASTER, what you have is a pool of resources, a pool of accelerators, a pool of maybe something like Octane memory, and you take those pools of resources and bring it to the compute node. Okay, so if you need 10 GPUs, then you'd say, I need 10 GPUs, and it composes it to the motherboard. And your program sees it as 10 GPUs directly attached to the motherboard. And for those that have programmed for running on multiple GPUs, you understand all too well that it is very difficult to program in distributed GPUs. This allows you to program multi-GPUs that are not distributed, that are attached to the motherboard. So if we compare what used to be legacy HPC and the modern HPC, when you purchase your high performance compute system, or when you purchase your server, your desktop, you're stuck with that hardware configuration unless you upgrade or make physical changes to the system. And that would be legacy HPC. It's built on, converged hardware. Whatever you buy is what you get, and it's fixed. Modern HPC, which is what Faster is designed to be, is built on, as I mentioned, the disaggregated hardware. So you can compose at will with the support of the composable software. So here are your pool of resources, and then you have a command center, and the user can grab what they need from this pool of resources. Okay, we're hoping to make this available to general researchers very soon. So in addition to Faster, we also have an NSF-funded grant, and this will allow us to deploy a machine that we are naming ACES, Accelerating Computing for Emerging Sciences. And this is a collaboration with 3 universities that's headed up by Texas A&M University and will be deployed here. So the ACES system is also going to deploy the composable hardware, but we're going to have a more diverse set of accelerators. So we still will have a lot of compute. It will have the composable infrastructure, and we will have these fast transfer data nodes, so you can transfer your data from remote areas to our machine for processing. So what's very exciting about ACES are the accelerators that we're going to be putting into it. So we're going to be putting graph core IPUs, intelligent processing units, FPGAs, cutting edge coprocessors like Next Silicon, NEC Vector Engine, the new Intel Ponte Vecchio GPU, which is slated to be available later this year, and the Intel Optane PCI SSDs for memory allocation, okay, large memory allocation. So we're very excited about this, and how I feel that this is going to be very useful for your digital twins is that you can compose the different accelerators together on a compute node and utilize them for building your digital twin. So you can develop your model using this composable infrastructure, and it can help you determine what you might need for your edge computing when you have fully developed your digital twin. Okay, so that way you're not trying to guess what kind of hardware you're going to need at the edge. You can test these things with the composable hardware with different accelerators, and then determine what you should need for your deployment at the edge that Walt was talking about. So a little bit more about the graph core IPUs. We have been testing these early on in preparation for deployment of ACES. So similar to the GPUs, they have a lot of compute cores, but it has a different architecture. Okay? And you see here, it has the same type of performance as a DGX A100 that comes from NVIDIA, but it does it at lower power consumption and lower heat. Okay, so if you do need something very powerful at the edge, the IPUs can be very beneficial. So in building your digital twin, if you're starting with a very complex model and you need a lot of compute power, you can start your builds, if it's very graphical in nature, through our portal. You can access the portal through a modern web browser, and it gives you the ability to run graphical programs without having to install specialized hardware on your system. And we have a lot of YouTube videos that cover how to utilize the portal. We already have a lot of software that's installed. So if you need some specific software, it's probably already there to help you build your digital twin. A little bit about our advanced support program. We have HPC analysts that can help you in your software development for your research workflow, workflow automation, okay, porting your applications to the cluster with these new accelerators. You will most likely have to port software. Standard applications like the AI ML workflows will probably already be ported, but you'll probably have to update your own Python algorithms, and we have people to help you with that. So if you're interested in learning more about our advanced support program, you can email help@hprc.tama.edu. We also have a lot of outreach. So if you're building a digital twin and you would like to collaborate with us, especially with our new accelerators that are coming on board, please reach out to us. We would love to work with you on that. If you want to teach a short course, if you're interested in joining any of our cyber teams, again, please reach out to us. You can email help@hprc.tama.edu, or you can find my contact information on our webpage. All things start on our webpage, right? So please visit hprc.tama.edu. Apply for an account. It's always better to get started earlier than later, because when you need it, you need it. All right, thank everyone for their time. If you have any questions, please feel free to unmute yourself, and I will answer to the best of my abilities.
Okay, seems we all know HPRC, so no more questions about that. So Lisa, there's one thing I want to mention about, it's the price tag for each system. I'm just wondering if you can tell us, the rough price for each system, so that we know how important, how precious those systems are, and how precious those facilities are for us to use it. Like a Grace, how much is it?
I actually don't remember the total cost of Grace. I know it's in the millions of dollars, but I don't know the exact millions of dollars number.
Yeah, I remember Grace is about $10 million price tag.
Somewhere around in there.
Faster is about 3 million.
Mm-hmm.
How about Esses? That's $5 million for hardware.
Yeah, 5+ million. Yeah, somewhere about there.
And 5 million for supporting other things. Yeah. So another thing needed to mention here, both Faster and Esses are funded by NSF, and
yes.
They have a national and even sometimes international impact. So if you have any research activities that you want to have this large-scale impact, getting linked to Esses and Faster projects will be a very good way to go. And we also have, I'm sorry, I'm still assuming I'm a part of HPRC, but I think I'm still am.
We consider you still part of HPRC also.
Yes, that's great. So there will be a lot of training programs, and I helped develop back then, when I was still working at HPRC. And there is now a bigger and bigger team providing all the services and supporting. And I'll be, glad if you need any help to get connected to all the folks over there, and I'll be glad to talk with you. And also Lisa will be here to talk with you about it. Yeah. Again, this is a very, very precious facility that HPRC is providing. The same with what is providing with ITC is for networking evaluation and testing. And here, HPRC is providing the computing facility, and it's crucial for a lot of applications, especially for digital twins on the simulation and prediction side. So you have Lisa's contact information. Feel free to reach out to her, and she will be very, very happy to talk with you about your project.
Absolutely.
Okay.